Hello everyone, thank you for stopping by to watch this video. I'm Angelina Mary Marcella from Bina Nusantara University who want to explain the research that my team has done about convolutional neural network algorithms for car accident classification. We have figured out the urgency of producing this research because according to World Health Organization data in 2019, a car accident has become the 10th leading cause of death in low to upper income countries. Also, around 1.3 million people lose their life because of this phenomenon. Some factors that might result in traffic injuries are increased driving speed, alcohol influence when driving, non-use of safety belt, dangerous road infrastructure, and poor traffic law enforcement. The probability of death may be increased if the victim receives a slow medical emergency. This has become a major problem when medical assistance takes too long to arrive because of the victim's survival rate can significantly change every minute. Moreover, the victim should experience severe injuries, economic problems, and mental pressure that often takes a long time to be healed. In addition, car accident cases keeps increasing year by year in the United States according to data from 2015 until 2021. These facts explain why the topic is important to be investigated. Many studies have done research in this field. They use various kinds of deep learning CNN models such as YOLO-CA, Inception V3, YOLO-V3, YOLO-V5, and RCNN. Some researchers also try to combine two models to produce a new architecture that can classify and detect car accidents. For instance, LSTM with CNN, Deep Walk with CNN, FPN with faster RCNN, and Random Forest with CNN. On top of that, another method is used in this field, which is hyperspectral image classification, which combines classifier fusion and data augmentation. There are several approaches that can be applied. The common one is binary classification, which classifies the data into two categories, accident or no accidents. However, others are using multi-class classification that classifies the condition into three or more categories, such as safe, dangerous, or crashed. Another study made a different approach by classifying the traffic condition into heavy, light, or traffic. In this research, we are going to compare three CNN models to classify images from CCTV into two classes, accident or no accident. The models that we compared are MobileNetV3-Large, EfficientNetV2L, and ResNet50. We want to find which model performs best for car accident classification. There are four main phases in this study. We started with dataset preparation, data preprocessing, algorithm implementation, and lastly, performance comparison by using four metrics: accuracy, precision, recall, and F1 score. To perform our experiment, we utilized car-on-the-road CCTV frames taken from Kaggle, collected by Charan Kumar, consisting of 989 images of accidents and no accidents conditions. 80% of the dataset is then split into a train set and 20% for the test set. Furthermore, the train set is randomly split again into a train set and validation set with a 80-20 ratio. Next, we preprocess the data by resizing them to 250 times 250 pixels since CNN models strictly receive images with a fixed size. Each pixel in the image is valued between 0 to 256. To reduce the complexity of the computation, we rescaled each pixel by dividing it into 255. In addition, we performed data augmentation to prevent the model from overfitting. Methods to generate augmented data in the study are rotating images randomly by 0.2 radians, zooming images by 0.2 times, and then changing the height and width image just by 0.2 times. After the data are ready to be used, it's time to put the algorithm into action. The MobileNetV3-Large architecture consists of three main layers: depth-wise separable convolutions, which is each input channel is filtered independently during depth-wise convolution, and then the expansion layer to create an expansion filtering compression mechanism. And lastly, the squeeze and excitation layers that assigns unequal weights to various input channels. It also applies some optimizer, such as neural net architectural search that optimize the accuracy of each block. Also, the net adapt algorithm to determine the number of filters for each layer. A study shows that MobileNetV3-Large has higher accuracy than MobileNetV3-Small because it has more layers. Hence, we chose MobileNetV3-Large for our study. Secondly, EfficientNetV2L is built in two main layers: mobile inverted bottleneck convolution layers, a residual block used for image models that use an inverted structure for efficiency, and the fuse and Markov layers. Optimizers that are applied are compound scaling, a scaling approach that uses a compound coefficient to scale the network's depth, width, and resolution. Also, the neural architectural search. According to a research, EfficientNetV2L gives higher accuracy than EfficientNetV2S and EfficientNetV2M. Therefore, our study used EfficientNetV2L. The last one is ResNet50, a variant of residual networks, whose architecture consisting of 50 convolutional layers. Features ResNet architecture is identity shortcut connection, which aims to keep gradient traffic as fluent as possible. The architecture consists of numerous sequential blocks, starting from pre-processing blocks, followed by 4 sequential blocks, with each block incorporated with a downsampling, and 2 ResNet residual blocks, eventually the fully connected output layers. Here is the result of our experiment. As mentioned before, the data is classified into 2 classes. The performance is measured by using 4 metrics: accuracy, precision, recall, and F1 score. We can see that the highest performance is held by ResNet50. It got the highest score for all 4 metrics: 95.2% of accuracy, 95.4% of precision, 94.94% of recall, and 95.13% of F1 score. The second best model is EfficientNetV2L, and the last one is MobileNetV3-Large. From this result, we can draw a conclusion that ResNet50 outperforms MobileNetV3-Large and EfficientNetV2L. The reason behind ResNet50 producing better performance over the other 2 models is related to its structure built up with residual blocks. This architecture has a direct connection that skips several levels in between. Skips connection have been proven to be able to maintain the network's learning parameters in deeper layers, hence creating a deeper and more effective way of analyzing complex patterns. To sum up, this experiment compares the performance of 3 CNN models, namely MobileNetV3-Large, EfficientNetV2L, and ResNet50 for car accident classification. Among these 3 models, ResNet50 achieved the highest result with 95.13% of F1 score. Thus, it proves that ResNet50 is the most effective CNN models for categorizing car accidents and offering insightful information for car accident prevention. Further research can explore potential areas including hybrid architectures combining multiple CNN models, transfer learning with pre-trained models, experimenting with large and more diverse datasets, and many more. That's all about this paper. Thank you for listening and see you next time.